So, good morning all of you. We were discussing on the technology and design overview of VLSI technology. Now, in the view graph you can see the cross section schematic of an NPN integrated transistors, and last time I have already discussed the difference between integrated and discrete transistors. In integrated monolithic transistors, the main feature is all the connections, that means either it is from base or emitter or collector or whatever it is, or substrate, all the connections are taken from the top surface of the chip. Here I had already explained the different regions of the cross section of this integrated NPN transistor, that is, this is isolation, this is the deep collector, this region 3 is extrinsic collector, and intrinsic base, this region 4, and region 5 is the extrinsic base. The extrinsic base is required for taking the contact from the base region. The main function of the transistors is controlled by the doping profile and the junction depths in the intrinsic region of these NPN transistor, that is this region, where you can get emitter, you can get base, the epitaxial and buried layer combination collector, and this is the P substrate. Okay. So, now this intrinsic base region is very important, and the doping profile in this particular region is going to govern the transistor parameters. So, now we know that the emitter region is highly doped and base is moderately doped, and the collector is also less doped, the epitaxial region. Now, we will see how the doping profile looks like. 1D doping profile, that means this surface is taken as a 0, and if we go deeper and deeper into the silicon, then we will see how the impurity profile changes. From this region surface to this, it will be the N plus dopant, that is here phosphorus. From this region to this region, that is the intrinsic base region, here it will be base in our transistor, and from this is the base collector junction, that means this particular point to this point is epitaxy, it is again N type dopants, and buried layer also N type dopants, the highly doped region. And the highly doped region, buried layer along with the highly doped the deep collector, the purpose is also explained earlier. So, now let us look into the doping profile, how it looks like. So, the doping profile is shown here. You can see this is a 0, and this point is the surface of the intrinsic region of the transistor, and from the surface, if we proceed towards the substrate, from the surface of the substrate towards the depth, vertical depth, if you proceed, then you will find that at the surface the doping concentration is of the order of 10 to the power 21. So, from there gradually it reduces, and this profile is something like complementary error function profile. We will discuss detail what is complementary error function profile or what is Gaussian profile in our diffusion lecture. Now, this from this region to this region is the N region, this is the N plus region, which is emitter region, and from here the base and emitter junction is at this particular point, that is the base junction, and again from here we find this is the basically the base doping profile, and in our case it is a boron profile is like something like that, and up here you can get this base to collector junction. This is the emitter junction, we can say emitter base junction, this is the base collector junction, and from the base collector junction then again the dopants are N type, and this is the phosphorus doped N type dopants are there, and this is epitaxy, this particular region, and from here again you can see here, if you go deeper into the substrate, you can see the doping level of N is increasing from this to this. Here the level is almost nearly 10 to the power it is more than 10 to the power 5 into 18. Okay. So, this is the buried layer. So, buried layer is highly doped region. So, in the cross section of the intrinsic cross section in the intrinsic region, the emitter is here of the order 10 to the 21, the base peak concentration is near about 5 into 10 to the power 17, and this is the epitaxy region. This is 5 into 10 to the power 15 or something like that, and after that it gradually increases. This is the buried layer. Now this particular profile, if you summarize, then we will find the different junction depths are shown here. Epitaxy is thickness is 5.2 micron, which is phosphorus dope, and 5 into 10 to the power 15 per cc. These parameters which I am showing here, these are typical values for a particular transistors, and these transistors FT is nearly 1 gigahertz, 800 megahertz to 1 gigahertz. So in this transistor you can see the buried layer is antimony doped, and this is implanted region, 80 keV energy, 1.5 into 10 to the power 15 per centimeter square is the dose. Emitter junction is 1.08, this point from surface to this point, this distance is 1.08 micron. Base junction, that means this is here, base to collector, that is 1.78 micron, and this 1.78 micron is from the surface. From here to here is 1.78 micron they are getting, and obviously the base width will be, intrinsic base width will be this base junction minus the emitter junction, then it is coming nearly 0.7 micron. That is the active base width, and this particular base width will decide your many of the transistor parameters, particularly the HFE or beta of the transistor. If this is thin, this particular base width is very thin, then beta will be extremely high, and doping level also will determine how the transistor property is will be achieved. Okay. Now the base junction is 1.78 as I told, then epitaxy to substrate, this is another junction. That means you see epitaxy buried layer you will not get any junction, because epitaxy n type dope and buried layer is also n type dope, so there is no junction. And junction you will get the buried layer and the substrate. Substrate is p type, and then n plus is the buried layer. So then there you will get the junction, and that junction is 9.42 micron. That is not shown in this particular diagram, because somewhere here, because I have take the plot from 0 to 6 micron and it is 9.42 micron. Okay. So these are the typical values of a particular NPN transistor which is used in earlier stages in ECL logic, but later on the geometry has gone down very much, and these parameters has again reduced very much, and obviously the performance of the at the moment the available ECL transistor is much better compared to the earlier version. Okay. So now let us see some configuration of the transistors. For example, you have seen many analog circuits where all the collectors are connected together, okay, and the emitters are different. One of the example I can say is in case of TTL logic gate, the first input transistors, multi-emitter transistors people are using. So there are so many inputs, multi-emitter and one base and one collector. That means several transistors, the collectors are common. Similarly, in any other analog applications, you may find that all the collectors are in common point and this is grounded. That may be the situation. In that case, it is economical if you combine all the collectors in one island, and emitters you can multiply during your design and fabrication, so that all the transistors which are connected, whose collectors are common, they can be fabricated in one block, in one island, and it will save a lot of space. So here I can show you one such structure. For example, here three transistors are there. So this is all the transistor, the base are individually separated, and this you see emitters are also separated, and but all the collectors are common, they are connected, isn't it? Three transistors here, base are different, emitters are different, but collectors are common. And in this particular case, in if you go for fabricating 3 transistors separately, it will take larger space or larger area on silicon. Rather, what we do here, you can see the collector, the one buried layer or one island is used to make all the transistors. Here the collector is one collector contact which is connected to the buried layer through deep collector, and different base region, this is one base region, this is another transistor base, this is another transistor base. So 3 bases are there and 3 base contacts are there, 1, 2 and 3, and 3 emitter contacts are also there, 1, 2 and 3. Okay, this is one structure where the collectors are connected together. So now in VLSI design, sometimes we need some cross unders. So what is meant by cross under? If you want to integrate many components and your technology does not permit multi-level of metallization, then it's all wiring or interconnection is done in one level of metallization, then the routing will be really a problem. That means you have to route your metal lines so that interconnection between undesired interconnection is avoided, isn't it? So in that situation, sometimes we take help of cross under. Okay, this is one thing, and another is a contact window. So all the regions, that means either it is base or emitter or collector or ground or substrate, whatever it is. So there you have to take a contact, metal contact, ohmic contact, and I explained earlier the ohmic contact and Schottky contact difference. Now in the contact window, how do you design a contact window? So this to here in this view graph you can see this is a contact window. That means after all the diffusion layers are fabricated, are made, then you have to grow a silicon dioxide and there you are opening a contact window, and this contact window in a both side of that particular region you have to allow some space. For example, here a 5 micron space in the left side and right side of the contact window has been allowed. The reason is, you see, this during your alignment, sometimes this alignment means when you are aligning mask of the contact window on the diffusion regions, so then there may be some tolerance, and that tolerance comes from the human error, machine error, etc. So if you can allow this side 5 micron, this side 5 micron, so even your alignment is not very accurate, it is shifted in this side little bit, this is little bit, then the contact window will not open in the combination of this region and this region. You have to ensure that window is just at the middle of this diffused layer. If this window is somewhere this region to this region, in that case you see this, say if it is a N diffused region and this region is P, so P and N all together connected in the contact, isn't it? And that may not be desired. So that's why in each contact window some tolerance is given, that is, this is in 5 micron technology, 5 micron. Nowadays you can reduce this tolerance also with much more sophisticated machine are available nowadays. Now there are again techniques available, self alignment, so alignment is automatic, then you may not have to allow much tolerance like that. Okay, this is one of the contact window design or structure. And now again you have seen that here the overlap of the metal on the oxide, this side and this side, nearly 2.5 micron. So this, if this is the 5 micron, so half of this space, half of this area is covered by the metal. Okay, so this is also very important, so that your contact window is covered from all sides using the metal film. Now this is the contact window dimensions, typicals are shown, and these dimensions are based on 5 micron process. Now this is another diagram you can see, this is a cross under. So what is cross under? Basically this cross under is used to ease out the the wall metallization routing. What is that? For example, you have to take a metal line from this point to this point, and at the same time vertical to the surface you have to take another metal line. This is vertical to the this is in this direction, left to right, and this is, you see, from the surface of the screen to back side, for example, perpendicular to this line. So if it is so, then there is, if this metal line passes from this and this is perpendicular to that, it will interconnect, short circuit will be made, isn't it? So then in order to avoid, what we normally do, in this isolated N AP region you diffuse a N plus region. N plus is highly doped, and highly doped region will give you a very less resistance. Is almost metal like conductivities can be obtained by very high doping level. Now we open a contact window here and here, then this metal line will end up here, and here again this metal line will contact in this contact window, so that here you can get a line, the conducting line from this, then it is coming here through N plus, and here again it is, this is a metal, and then again the current is flowing in this direction. Then from this point to this point you will get a clear gap, and this gap is what? The top is the oxide layer, silicon dioxide, and in this silicon dioxide another line can cross easily. This is known as cross under or underpass. That means this metal line goes here to here, the current flows in this direction. So in the blank region here, another metal line which is perpendicular to this metal line can pass through. That can avoid the complexity of the metal routing if you are confined your design into single level of metallization. Is clear? So now next again I will show you some other configuration of the bipolar transistors. Here the 4 configurations have been shown in this view graph, and the position of the collector contact and emitter contacts are different in this 4 configuration. For example, here you see the collector is a horseshoe type, and this is emitter, this is the base contact, and this is the base region. Here one of the advantages, the collector contact window you can open either in this arm, you can open in this arm, or you can open in this arm. This is the diffuse collector region, deep collector region, for example, and that also helps the wiring or the metal wiring, means the routing. For example, some transistors you can take contact from this side in this direction, some transistor you can open the contact window this side and you can take contact in this direction, and another you can take contact in this direction. Here one of the advantages is that the carriers which are collected, and for example the emitter injecting, and through base the carriers are moving towards the collector, and collector is collecting the carriers. So that collection will be done surrounding this base region, not in the one region. So that is one advantage. So the collection of the carriers will be done efficiently surrounding the all region or surrounding the emitter region. Okay, and another is the wiring. You can take the interconnect lines from the collector, either this or this. Freedom is there. Now, if you concentrate in this figure, you see there are 2 deep collectors and 2 emitter, 1 base contact. Okay, that is 2 emitter. Sometimes for increasing the performance or to have better performance of the transistors, the 2 emitters are made, emitter contact, and these 2 emitters are joined together here in a metal line, and 1 emitter contact is taken here, metal line is here. From base is taken in this direction, base contact, and collector also you can combine these 2 collector together, and you can have the collector routing line, you can draw either here and there. Okay, so two emitter contact, or sometimes we use the two base, one emitter, two base, two emitter, three base, like that, when we go for high frequency transistors. So there sometimes this sort of structures are very much useful in order to increase the FT values. High frequency transistors, main emphasis should be to reduce the parasitic capacitance and other things, other parasitic components, so that frequency FT or frequency operation will be high. So this sort of structure can reduce many of the parasitic components like capacitance and resistances. Now here another structure is shown. You can see here collector is 1, base contact is 1, and there are 3 emitter contacts. Okay. So 3 emitter is connected. You see 3 emitter, one base is there, not different. In earlier in one diagram I showed you, the 3 base contacts are also different. Now here the base contact is the same base region, you are diffusing the 3 region, N region emitter, and you can use as a one collector, one base, 3 emitter transistor. That is the TTL gate, the first transistor, input transistors are like that. Base contact, base 1, one collector, and emitters are multiple emitters, multi-emitter transistors, isn't it? So this in those cases this sort of configuration is used. That means in one island you are getting 3 transistors here. Similarly here in one island you are getting 2 transistors. Here difference between this and this structure is that third and fourth structure is that here the 2 base are diffused. Here you see this is one base and this is another base, but here in one base 3 emitters are fabricated, but here base and emitters are different, but collector is common, similar to the earlier transistors, common collector transistors. Okay. So these 4 configurations, any of the configuration you can choose depending on your applications. Okay. Now I will discuss on the progress of the transistor geometries from planar to isoplanar 2. The planar structure already I explained, that means this structure is a planar, you can see. So that means here the emitter is there, this is the base, this is your buried layer, and this is the epitaxy, and this is the P isolation. Now you see in the P isolation, since it is a deep isolation, a deep diffusion from surface, this isolation region should reach up to the substrate. So you have to diffuse a very long time, and if you diffuse for a long time, that means dopants will also move laterally. So dopant, if you diffuse for a longer time, it not only moves downward vertically, but also it moves laterally. So lot of lateral space of the transistor will be consumed by this isolation diffusion region as well as deep collector region, because there is a long time diffusion. That means in this sort of structures you have to allow lot of space between the isolation to the base region, this space, which is not required in the second structure. If you go for isolation not by diffusion isolation, p-n junction isolation, if you go for oxide isolation, I will discuss in detail oxide isolation later class, and another isolation is known as the LOCOS, local oxidation of silicon, that is oxide isolation or dielectric isolation. So there instead of p-n junction you can open here a trench, and there you fill the trench with oxide, or you can grow native oxide from surface up to this, so that silicon dioxide is a insulator. You see here is shown is silicon dioxide, this side is silicon dioxide. So if you isolate one transistor to the neighboring transistors by this oxide layer, then the extra lateral space which required in planar technology is not required in this particular case, is isoplanar, that is in oxide isolated bipolar transistor. So automatically the geometry of the transistor can be reduced, and a comparative the dimension of the three configurations is shown here. So you see, if a planar structure looks like this, then isoplanar has been reduced both the lengthwise and widthwise. And in isoplanar 2 is the improved version of the isoplanar, and there sometimes we use, you see, self-aligned technology, and that means for alignment of emitter inside the base, I had to leave some of the space here and some of the space here in isoplanar configuration. But in this case, you see here, this is emitter, this is the base, and this is the collector. No space is allowed for alignment tolerance. That means the space required for alignment tolerance has been completely removed in isoplanar 2 process, where we can use self alignment technology, automatic alignment. So how it can be achieved, that also I will explain in the VLSI process sequence, some of the advanced VLSI process sequence topics. There I will explain everything. Okay. Now, planar to isoplanar 2, the gradually improvement is there, and automatically you can see the area are shrinking gradually with the use of improved process technology. Next slide, I will explain on the resistances, how to fabricate resistance. Other than the transistors, either it is a MOSFET or BJT, resistances are also required in a IC, in different ICs. Without resistance, the circuit will not be complete. Okay? And sometimes capacitances are also required. But in the recent design, you have to see the capacitances are as minimum as possible. Large values of capacitance are very difficult to fabricate in monolithic IC, because they will take a larger amount of space. And you have seen if larger capacitance, if you go for parallel capacitance, there it depends on the area, isn't it? The two metal plates are separated by dielectric, and the area of the metal plate will give you the capacitance values as well as the thickness of the dielectric film. So if you use larger area for capacitance, so you cannot shrink the device dimension. So that's why the capacitances are normally avoided in the VLSI design. We use transistors and resistances, and if sometimes required, some small capacitance can be made from the metal oxide semiconductor CMOS structure, CMOS capacitance may be used in some cases, not always. But resistances are must, and again I will show you that the area required by the resistances are large compared to the area required by transistors. That is another feature. So that means a good design is that one where lot of transistors are there, but resistors numbers are as small as possible. Okay. Now, this is the structure of the resistances, and in a VLSI, the resistances are formed along with transistor. For resistance, no extra diffusion step is used. In a transistor, you have seen the major two diffusion steps are, one is base diffusion and another is emitter diffusion. The emitter diffusion is a high concentration diffusion, N plus region, and base is moderate concentration. Okay. So, if high concentration means their resistance value will be very low, and low concentration base will give you high value of resistances. That is why when you need the low values of resistance in the range of say 10 ohms, say 100 ohms, or say 200 ohms maximum, so there you can utilize the emitter diffusion region as resistance. But if you need moderate to high values of resistance, for example 1 kilo ohm to say 10 kilo ohms or say 50 kilo ohms, in those cases we use base diffused layer as resistance. Clear? If you need much higher values of the order of say megohm ranges and higher, then some other techniques is used. One is the pinched base resistance. I will explain what is pinched base, and another is epitaxy layer. Epitaxy layer doping level is less compared to the base, so it can offer larger value of resistances. In some cases, epitaxy layer is also used for making or for fabricating high resistance values. So now, but the most of the resistances which used in circuits are in the value of say 1 kilo ohm to 10 kilo ohm, in that ranges. So if it is in that range, we will always use the base diffuse layer for making the resistances. Then how do you design those resistances? How it works, let me first explain that part. So you see here, just like a transistor, as I told you, the resistances are made along with transistors. Same steps will follow for making the resistances. So buried layer, then epitaxy, then P plus isolation here, all is done along with the base, along with the diffusion of the isolation, buried layer, etc., along with the transistors. And after that, when island is created, along with base, the resistant diffusion is also made. Clear? Just like base diffusion, resistor P diffusion is done here, and there after that we don't diffuse any emitter here. Okay, rather you open a contact here and in this region another. So now from here to here it will form a diffuse resistance. For example, the current will flow from this contact to from this direction and end up here, and then again here metal line will pass. So that means this diffuse region here, it will form a resistance, is a semiconductor resistance. Diffused semiconductor region will give you a resistance value, and for different values of the resistances you have to increase the length of this diffuse semiconductor region, isn't it? Now how do you calculate for particular values of resistance how much will be the length and how much will be the width? So for that calculation I have shown here the top geometries. This is a cross sectional view, and if you see the top view of the resistances, that means the geometry of the structure of the resistances, it looks like this. So this is one contact window, this is another contact window, like here is one contact, here is another contact. So in this particular case you see the inner region, this line is the diffuse region, and there at the end the diffuse region is increased to take contact from this point to this point. Okay, and the estimation of resistances is done from the normal values of you can see, let me see here. So we know in a semiconductor bar the resistance R is given by rho into L by A. L is the length. If you see a resistance like this, a structure like this, so this is a semiconductor bar and this length is L, and this is the cross sectional area is here, this is the cross section area A, and if the current flow is here like this, so the resistance if it is the R, so R is equal to rho into L by A, isn't it? The L is the length and A is the cross sectional area. And what is the cross sectional area? This is this the one is width into thickness, isn't it? That means it is equal to rho into L divided by width is the W into thickness is the T. Thickness means the height I am telling. Okay, Now, if you write the R is equal to rho into the L by W, L by W is a number of square. I can say the rho by T into L by W. What is L? L is this length and this is the W. So that means this is L and this is W. So L by W will give you the number of squares. How many squares are there? L by W, isn't it? Number of squares you will get it. Now the rho by T, rho is the resistivity, isn't it? Resistivity. We can write the R is equal to rho by T, I wrote it as rho square, into L by W is the number of squares. This rho square, what is the dimension of rho? Ohm centimeter, and the T thickness, it is also centimeter. So ohm centimeter by centimeter, it is only ohm. So that means the rho square is known as seat resistance. Seat resistance, and this seat resistance, if I know, and that is basically rho by T. Rho is the resistivity and T is the thickness of this semiconductor, the bar, and in this case the thickness of this diffuse layer, from here to here is the thickness, vertical, and in this view graph you can see length is from this region to this region is the length, and width is from this point to this point, this is the width. Okay. So now total resistance value, we can get the seat resistance multiplied by the number of squares. So the seat resistance is determined from the doping level, isn't it? If the doping level is very high, then the resistivity will be very low, and automatically the seat resistance will be very low. Okay. And then multiplied by the number of square, which is dependent on our design. So then that will give you the total value of the resistance. So the rho square or seat resistance is one important parameter of any diffuse layer. Always the T value is not measured, because it is very difficult to measure how much is the junction depth. It involves some rigorous process. So in order to avoid the measurement of T, the seat resistance from the surface of the silicon diffuse region can be measured by using the 4-point probe resistivity instrument meter. 4-point probe resistivity meter is available. So using that machine directly, you can get the seat resistance of that particular diffuse layer. And typical value of the seat resistance in normal base diffusion is in the range of 240 to 50 ohm per square, and the RS is the seat resistance. This is known as the RS. So you can write R is equal to RS, which is rho square, into the number of square. So this is one important relation by which you can design the resistance values. Okay. Now here the RS into L by W, L by W is the number of squares. Now for large value of resistance, for example here it is shown, this is 10K, 5.6K, this 2.2K. So 2.2K is a 256 micron is the length, because the width is fixed here, which is maybe 10 micron or something like that. So now similarly for 5.6K, the total length is 653 micron, and similarly for 10K, total length will be 1166 micron if you use the RS value 240 ohm per square. So now if you need very large length, so it will take a larger area of the silicon chip. So what normally we do, we use these bent lines, and sometimes meander line structures also used. What is the meander line structure? Meander line structure is okay. this is something like this, it will come like this. Okay. So these are this sort of Nandyal structure sometimes is used in order to reduce the area required for fabrication of that particular transistors. Okay. Now this is in this way we can if you change the RS value, seed resistance, for emitter diffusion it is different, for base diffusion it is different, and depending of the requirement of the range of resistance values we can select it. So next, these are the resistor geometries, and I will now give you one example of the layout design of a particular circuit, and this is the circuit is I think known to you. Can you tell me what is this circuit? Yeah, right, TTL NAND gate. So it is a very popular and well known circuit, and how this circuit we will go for design in monolithic version, let us see. So now in the next step, first what you are doing, what we have done, so we have just placed different transistors and resistances so that it will take a minimum area. So you see this transistor is used here, and this resistance, one resistance 4K resistance is fabricated here, the 1K small length is here, similarly T2, T4 is here, T2 here and T4 here, and T3 transistor which is this one here, and this diode is here and output is taken here. And when I am placing these components, we have to one thing keep in mind, that ground point and supply point should not be side by side. You see the ground is taken in the top side here in your view graph, and the VCC is in the bottom side here, just opposite direction. That is one point. These are the input points and this is the output point, and we have to also see whether inputs and outputs should not be very near. So in that case maybe there is some coupling, you can get some energy coupling may be obtained. So in order to avoid that we have to see those points. And now after placement of the components, then routing means interconnection of the different lines. So the interconnection of the different lines are made such that there is no short circuiting. For example, here one line is passing here, but this resistance from here to here is diffuser, we are taking contact in this region and this region. So in between there is a dielectric silicon dioxide. On silicon dioxide the metal line can pass, there is no problem. Because in earlier view graph you can see the resistance, so the contact is from this point to this point, but in between this region is a dielectric, this is silicon dioxide. So another line can pass from this side to this side, can pass easily. So that is shown here, you can see. So this resistance from this point a metal line passes here. And if you now see the complete TTL complete layout of this TTL NAND gate is shown like this. Complete layout means after fabrication it looks like this. So this is the bonding pads. So these are the 4 inputs, 1, 2, 3 and 4, and the pad for ground is here, the pad for VCC is here, and the pad for output is here. These are all bonding pads. Okay. So from circuit to placement and routing, and then the complete the photograph of the chip is shown here. So now next step I will discuss the fabrication, total fabrication in a nutshell, starting from this ingot, means the silicon crystal making, to the packaging. What is the steps? At the beginning one view graph I showed you the design, starting from the floor design to the to different sequences, then comes fabrication and then comes packaging. Now only the fabrication part, wafer preparation part is elaborated in this view graph. Now you see ingot means silicon, from the silicon melt using the Jochalki's technique or float zone technique, we make the silicon ingot, that means semiconductor bar. So this is made slices here, okay, small size, then you polish it, then you will get the silicon wafer, and this silicon wafer now is ready for processing. And in this processing, the one part you can see here which is a furnace or some implantation equipment is used here. So that is for oxidation, making silicon dioxide, for diffusion of impurity atoms, for getting diffuse layer. Then comes implant, it is also for incorporation of impurity atoms. Then evaporation, deposition of metal films or some other semiconducting films also you can make here, deposition. So this is this step. Then comes here is the lithography. This is the mask. From mask you can transfer the pattern on the substrate here. Then comes the etching and you will get the windows, and after windows again you go for diffusion. So these steps actually repeats for different mask layers. In your BJT transistors, so buried layer 1 mask, then isolation 1 mask, deep collector 1 mask. Each mask is here, the windows is formed and diffusion is taken place, then again comes back. So this cycle continues until and unless all layers are formed, and then you get the metal interconnection. After that it is coming here the finished wafer, and there you can see some pins are coming, and using these pins we are testing the chips. That is wafer level testing. And in this wafer level testing we select the good chips, and then it comes here the dice. This is the dice. So this dice already the good chips are marked, and then you have separated the dice. It is shown here in a expanded version. You see the each square is a small chip, and that looks like here. So whole wafer here you can have, at the same time millions of transistors are there in the big wafer, say 8-inch diameter wafer. Now separate each transistors or each ICs, and this each IC is then called a dice. This dice is attached on the die attach. This is the housing, okay. And this small die, what you get from this wafer is of dimension say 0.1 to 1 centimeter in that, and in this IC 10 to the power say 3 to 10 to the power 6 or something like that is component. Nowadays VLSI you can easily fabricate. So now this die is again kind of bonded, because these are pins, and all the pins the bonding is being made, okay. After bonding of the pin, then it is encapsulated. The complete encapsulation is being done, and then you get the complete chip. Though starting from the ingot or silicon bar preparation to the packaged chip, these are the steps followed. And here we will discuss each step one by one, except this semiconductor crystal, single crystal wafer fabrication. So that is the wafers is available, we assume, and from the wafer how the each steps is used to get different layers, and then how packaging is being done, how bonding is being done, that in this course I will explain in detail, that individual unit processes, okay. So next class, with the contents of this VLSI technology course I will start, and then I will discuss the first topic, that is the contamination and clean rooms environment, okay. Thank you.
Let me now show you our class 10 clean room and the laminar flow workstations. In this room we carry out the photolithography operation. This is an extremely critical step in the VLSI process, where a high level of cleanliness is given prime importance. All work is carried out in a class 10 laminar flow workstation. Please note that the light used inside this room is yellow. Some major equipment here are a mask aligner and a photoresist spinner. What you now see is a mask alignment machine. This is used to align the required pattern on the mask with the wafer. This aligner can align to even features less than 1 micrometer. You can now have a look at the Gyrex pattern generator. This is a mask making machine. A layout editor like LASSI is used to generate a pattern file. The data generator program converts it into a format that is acceptable to the Gyrex pattern generator. Inside the pattern generator, we expose an emulsitone or bromide coated glass plate to programmed periodic flashes of a xenon lamp. This is how a mask is generated on a glass plate.